everybody. How about if we get things underway this morning? Let me start today with just a few sort of administrative things, right? Nothing about biology per se, but stuff I need to tell you. The labs for this class start this week, right? So quite a few of you emailed me just to make really sure last week that there were no labs. A few of you have already started to email me to make sure that this week there are labs. Let me just settle the issue right now as best as I can. The labs for this class start this week, right? So if you have a Tuesday lab section, today is your day, all right? So all of you will be in a lab at some point during the course of the week. I've been promising that I would tell you, I'd check with the prep lab people to find out what it is they wanted you to bring in terms of attire and equipment and such. It's pretty straightforward. It turns out that there is a dress code that they want to enforce starting on day one, right? And the dress code is pretty much this. They want you to wear pants as opposed to shorts or short skirts, right? They want you to protect your legs from things that might get spilled on them, okay? So they want you to wear pants, no open-toed, let me do this one again, no open-toed shoes, all right? So sandals probably wouldn't be a good idea, again, in case you might spill something on yourself. And no tank tops. I think that's aimed at the women in the class more than the men, but, you know, who am I to say? So, but no tank tops. And again, it's just to protect your body with a layer of clothing in case something got spilled on it. The one piece of equipment that they want you all to bring for yourself are goggles, right? And goggles are available for sale at any of a number of places, including the university's bookstore. In the past, they have been kind of cool about that the first week, in that they might have a few extra pair that they can loan to people. I wouldn't count on that. Some years ago, they weren't quite so cool. They would actually rent them to you for like $5 a goggle, and if you didn't give them the $5, they made you leave. So just bring goggles, right? Because I don't know if they're going to be cool or not cool at the labs this year. When we first met a week ago today, I said something about maybe needing a lab coat and gloves, that sort of thing. They're being super cool about that this year. No need for a lab coat. And on those occasions when you need gloves, gloves will be provided. I have been able to prevail upon them that they should actually do something for you with the lab fees that you pay, right? So your lab fees are paid for some of the reagents that will be used, but more importantly, I think they're paying for your gloves. So again, bottom line, you need to have pants, shoes, a shirt that has sleeves would be best, and goggles. You also should take this lab manual with you. And I said this at the first time we met. Please read the experiment, the first experiment. We're going to go through them in order. Read the first experiment before you get to lab. It's going to make it a lot easier for you when you're in the lab. You'll get done quicker, you'll get out of there faster, and you'll get more out of it if you read the experiment before you go in. I'm thinking 10 minutes is what you should allot to read through this experiment. You don't need to commit it to memory. There's not going to be a quiz on it. Just be familiar with what it is you're going to be doing and start to formulate in your head a strategy for marching through the different steps of the lab. All right? So that's the deal for this week's labs. Again, they all start this week. In the labs, you're going to meet your graduate teaching assistant for the lab sections. You'll get to know those teaching assistants pretty well during the course of the semester. They're the folks who are going to be grading your lab quizzes and your lab reports and the questions that you'll be answering during the course of the experiments in the lab. So get to know those folks. I would also suggest that you think of them as a resource for the content in this class. They all have the textbook, they all have the lecture notes. I've encouraged them all to sort of follow along with what's going on during the course of the lectures. So if I say something that has you puzzled and you have a hard time getting a hold of me, maybe you'll have better luck getting a hold of the teaching assistant for your lab. Again, think of them as a resource that way. All right, question? In the lab this week, you'll probably, I hope, I'm going to encourage, I'll remind the TAs to have you fill out the section. There's a couple questions there about yourself, is what it comes down to. You don't have to do that in advance. You can save yourself a couple of minutes if you do it before you go. And I tell you what, if the TAs forget to ask the class to do that, why don't you remind them that they're supposed to have you guys fill that stuff out. That's my single best chance to get to know you guys, to read through those things. So I read through them. It's also helpful for the TAs to know where you're coming from and what you are expecting in these labs. Okay, so that's the story for the labs. One other question. I did say goggles, and I hear you, and I wonder myself. Each year we have a different crop of people working in the prep lab, and how they define eye protection changes from one year to the next. I am surprisingly out of the loop on that sort of thing. I design the experiments, I say make them work, and I walk away. So I know goggles will work. I would think that my glasses would work, right? But it's not my final decision. Goggles I know will work. All right? If you have a problem with the prep lab people this week, there are later sections unless your lab meets on Friday. So if they are turning you away, just plan on coming to a later lab section, and there will be flexibility built in this first week to accommodate that sort of thing. But this is a really safe first experiment. They're all very safe, but this one's not especially dangerous in any way, so they should be able to cut you all a little slack during the course of this first week. All right, a couple other things quickly. I spent 35 minutes today sitting at my computer waiting for somebody to use the virtual office hours that I've got. So nobody came. And it makes me wonder if I didn't know how to use the virtual office hours, but I think it's more likely that you all just forgot that I have virtual office hours. In the future, Tuesday and Thursday mornings, my plan is to hang out on Pilot Live for this course from about 9 o'clock until about 9:20. Right? So if you have some questions, you can let some feedback from me just before we get class started. And if you don't want to come to class or Wright State's campus, that's a great opportunity for you to get a hold of me. So again, just a reminder. If you want to use Pilot Live, let me just give you one suggestion. Set up in Pilot Live for this course, there is one virtual office hour that is on in perpetuity, right, from the day that the class first met to the time of the final exam. That's there. It's called the test virtual office hours. That's there for you guys to check out the equipment on your end, to make sure you have the software and such that you need. So if you want to use those virtual office hours, it might be a good idea to do the test virtual office hours sometime before you try to do it for real, because if you're struggling to get into the virtual office hours, I won't be able to answer any questions that you have because you can't get into the virtual office hours. Right? But so the test should let you work all that stuff out. You'll probably have to install a little bit of software to get it all up and running. And again, you'll be talked through that with the virtual office hours. Lastly, it's my understanding that the issue with the audio for the Tegrity recordings for this class has been sorted out. So keep our fingers crossed, and we'll check later this afternoon to see if this lecture's audio is being captured better than the last couple. Apparently there had been some problems with Tegrity that required some computer software to be restarted and reinitialized, and they neglected to do that to the computer in this room, but that now seems to have been taken care of. So hopefully the audio for this lecture will be captured a little bit better than it has been for the last two lectures. For both the first and the second lecture of the course, we do have complete transcripts of every silly word that I said. And so I don't know, that may be a reasonably good substitute for the audio associated with those lectures. I think they may actually be more valuable because they're in a Word file and you can just search for keywords, all right, and get right to the thing that you're interested in hearing what I had to talk about. All right, So I think that's all the administrative stuff I needed to talk with you about. Remember, labs start this week, all right? Come with your lab manual and a pair of goggles, and you should be good to go. Then, it's time to get to work and talk about some biology stuff. You can see from the outline behind me here that today's lecture is still going to be one about chemistry. Thursday's lecture, I talked with you about what I would call inorganic chemistry. It's essentially the entirety of the freshman biology series in a nutshell is what I talked with you about on Thursday. No mean feat, right? Pretty slick stuff there. All the stuff you're going to be doing in freshman chemistry this year now is going to be anticlimactic because the important stuff, the good stuff, is all out of the way. I don't know, I think, in all modesty, I think it says something about the quality of instruction that you get from a biology professor as opposed to a chemistry professor. Just one more instance where we should be having you guys think seriously about being biology majors as opposed to chemistry majors. But, that's my personal opinion. But so that was inorganic chemistry. Today, we're still talking about some things that are inorganic chemistry in a strict sense, but I want to focus our attention today on the chemistry that's associated with water. Okay, so it's not an organic compound, but boy, water is such a fundamentally important molecule to life as we understand it on this planet that it is actually hard. I'm inclined to say it's not possible for biologists to conceive of or to imagine life existing in the absence of water. Right? And that permeates all sorts of things in terms of the science, the enterprise of science in this world. For instance, NASA, when it's looking for extraterrestrial, that's the thing that they're really excited about, is looking for something, some other example of life. Their first idea, their first priority is go where the water is, right? Because again, it's inconceivable to us that life could exist in the absence of water. So that's why certain moons of Jupiter and Saturn are targeted for probes that'll get there in another 15, 20 years, because those are the moons where there's a good indication that liquid water in particular is likely to be found. And where there's liquid water, we think there may be a chance that we'll find some life. Again, because we can't really imagine life in the absence of water. And so what I want to do with you today is talk with you about what it is that makes water so very special in that way. It's a remarkable molecule for a list of reasons, right? Its specific heat, its ability to act as a temperature buffer, its ability to act as a solvent, and other things. These things are fairly unique to water. I want to walk you through each of those features today, that list of things, and then along the way in the absence of this feature, if water wasn't able to do this, then life would have a hard time. But water can do this, and living things take advantage of that in a way that no other molecule can work as a substitute. It's a remarkable molecule. It's hard to imagine a molecule that could take its place. Right? So that's the plan for today. I want to talk with you about the chemistry associated with water. And then on Thursday of this week, we're going to round out all of the discussions about chemistry by my finally getting to talk with you about organic chemistry. It's usually a sophomore level class in most chemistry curricula. And in the span of one lecture on Thursday, I'll take you through all of what's important in sophomore chemistry at a place like Wright State. That'll be organic chemistry. In a nutshell, organic chemistry is the chemistry of carbon. Right? So today we're focusing on the chemistry of water. Thursday we'll talk about the chemistry of carbon, and then we'll talk about how we put all of these things together, the organic compounds, the water, and so forth, to make some really cool structures that are important for living things. And that'll be a week from today. All right, so today, the chemistry of water. Let's start by just having a quick refresher of some of the most important details from that lecture on Thursday of last week. Remember this idea of valence. I told you, I'd like for you all to remember, that is the number of unpaired electrons in the outermost shell of an atom's orbitals. Right? The number of unpaired electrons, that's really the key concept. And that in turn dictates how many covalent bonds a particular atom wants to be engaged in. Okay? So if you look back up here on this slide, you'll see hydrogen has a valence of 1. It's got one unpaired electron in its outermost shell, the 1s orbital. Okay? That means it wants to make one covalent bond. If you ever find yourself contemplating what sort of molecules would have hydrogen involved in two covalent bonds, just save yourself some time. Stop thinking hydrogen does not make two covalent bonds. It only makes one. It has a valence of 1. That's it, period. Okay? In contrast, if you look a little bit further, I guess, to your right, oxygen has a valence of 2. There are 2 unpaired electrons in the outermost shell of oxygen atoms' electron orbitals. Okay? Two pairs of paired electrons, but 2 unpaired ones. Those are really what our focus is on. Valence is the number of unpaired electrons. Oxygen likes to make 2 covalent bonds. It has a valence of 2. Nitrogen, a valence of 3, likes to make 3 covalent bonds. And carbon, with a valence of 4, likes to make 4 covalent bonds. Okay? There's also this idea of electronegativity that I tossed out kind of close to the end of the lecture on Thursday. Electronegativity is sort of in a word capturing this idea that some atoms have a greater affinity for electrons than others do. Okay? Hydrogen, and that affinity for electrons is ultimately rooted in a rule, maybe an obsession, that nature has. Right? Nature really likes for atoms to have their outermost shell of electrons either completely full with electrons or completely empty. Hydrogen is half empty if you're a pessimist, or half full if you're an optimist. Right? Glass of water, half empty, half full. I don't know. But hydrogen there can go either way. Hydrogen is just as happy, just as comfortable shedding one of those its one electron, as it is in taking another electron on. Getting rid of the electron empties its outermost shell. Nature likes that. Taking on an electron fills its outermost shell. Nature likes that. It can go either way. It really doesn't care. If you have 2 hydrogen atoms sharing each of their electrons, you've made one covalent bond, and part of the time, one of those hydrogen atoms will have both of the electrons. Its outermost shell will be completely full, and the other one will have neither of the electrons. Its outermost shell will be completely empty. Both of them will be happy. In the converse, they'll both be happy. When the one that had none now has 2, its outermost shell is completely full, and the one that had 2 now has 0. Its outermost shell is completely empty. That's a nice, happy situation. Nature likes that. And when the electrons are in transit between the 2, that's okay too. It won't last that long. Right? So hydrogen, when it forms a covalent bond with another hydrogen atom, has a really nice, happy, stable, comfortable relationship where the electrons are equally shared. Hydrogen atoms have the same electronegativity as other hydrogen atoms. That means there's sharing of the electrons. When the electrons are equally shared between 2 atoms in a covalent bond, we have a special name for that kind of covalent bond. That's called a non-polar covalent bond. Now, I didn't mention that word to you on Thursday. I might have forgotten. Let me more charitably say that I felt I had already thrown too much at you, and I wanted to wait till today for effect. All right? You guys decide which is the reality. I think is probably the first. But when 2 atoms are sharing electrons equally, that's called a non-polar covalent bond. When 2 atoms don't share the electrons equally, there's going to have to be a different word that we use. If sharing of the electrons is nonpolar, what do you suppose unequal sharing is called? That's a polar bond. Okay? Water, H2O, two covalent bonds that connect one hydrogen to an oxygen and another hydrogen to an oxygen. Water's covalent bonds are a very good example of polar covalent bonds. You'll remember, the next slide will help me show you. You'll remember that water, because of that unequal sharing of electrons, oxygen is an electronegative atom, certainly relative to hydrogen. Hydrogen can take electrons or leave them, it doesn't care. Oxygen wants to bring electrons toward itself. It wants to acquire electrons as opposed to getting rid of them. Why? Philosophically here, what's going on is to fill its outermost shell, it just needs to pull in 2 electrons. To empty its outermost shell, it would have to dish off 6. It's a harder job than bringing in 2, so water has a preference, oxygen has a preference for bringing on electrons as opposed to getting rid of them. Because oxygen is more electronegative than hydrogen, the electrons in this covalent bond, shown by that one solid line, the electrons in that covalent bond, on average, spend more time close to the oxygen than they do to the hydrogen. This is a polar covalent bond. There is a sharing of electrons. That hydrogen does make it out to the hydrogen once in a while, but more often it's close to the oxygen. Okay? A polar covalent bond, again, is a covalent bond between 2 atoms with different electronegativities that cause non-equal sharing of the electron. A polar covalent bond will always have associated with it a partial charge or a separation of charge. Here, because the electron with its negative charge is by the oxygen more than it is by the hydrogen gets a little bit of a flavor of a positive charge. You got that proton not being shielded all the time by an offsetting negative charge from the electron, so that hydrogen part of the water molecule has a partial positive charge. That's what that little squiggle that the arrow is sitting on top of, move it. That little squiggle is the lowercase Greek letter delta. And chemists use that to, in shorthand, say partial. So that little lowercase Greek letter delta means there's a partial positive charge there, because this is a polar covalent bond. And the oxygen, because it's got that electron, the negatively charged electron hanging out with it a little bit more than the hydrogen, the oxygen gets a partial negative charge. So for a nonpolar covalent bond, there's equal sharing of electrons, and there is no appreciable separation of charge across the atoms involved in that covalent bond. For a polar covalent bond, there is unequal sharing of electrons, and we do get this partial separation of charge. When you look at a water molecule, there's an awful lot of these squiggles, right? There's an awful lot of these positives, partial positive, partial negative, and partial positive charges. Each water molecule has on its surface portions, regions, patches, whatever you like, that have a little bit of charge associated with them. In terms of density of regions or patches with partial positive or negative charges on the surface of the water molecule, it's hard to find a molecule that has a higher density. Right? Water molecules, their whole surface is this little patchwork of a little bit of positive charge, a little bit of negative charge, a little bit of positive, and a little bit of negative. And that's pretty unusual as far as molecules go. We'll get to see some other molecules later in today's lecture. But that's pretty unusual. And again, that's going to ultimately be something that's going to really govern what it is that makes water such a special molecule. Now, this figure, which I threw at you in class on Thursday, I used it to illustrate the concept of a hydrogen bond. Hydrogen bonds are weak interactions between molecules. There is no sharing of electrons, but that little bit of a negative charge on one water molecule likes to rub up against the little bit of a positive charge on another water molecule, and both of them feel good. Opposites attract, right? So they nestle up against each other. And because water has this patchwork of 4 partial charges, 2 positive and 2 negative, every water molecule likes to make 4 hydrogen bonds, okay? Because it's got 4 of these itches that need to be scratched, okay? 2 little positive itches that need to be scratched by cozying up against something with a little bit of negative charge, and 2 negative charges, 2 partial negative charges that really only feel right when they're cozying up against something with a little bit of positive charge. Every water molecule is happiest, it's most comfortable, nature is most pleased when water molecules are engaged in 4 hydrogen bonds each. Picture this at a molecular level. I mean, this is a start, this image here. Picture this at a molecular level, because you got one water molecule in the center there that's got sort of a loose affinity, a connection to 4 other water molecules. Each of those 4 other water molecules is going to have a loose affinity with 3 other water molecules. They're all interconnected. And then each of those other water molecules are going to have 4 connections with water molecules. In a watery puddle, right, all of the water molecules are loosely connected to each other. That turns out to be pretty huge in terms of the chemistry associated with water. That connectivity between water molecules is ultimately what's responsible for water's cohesiveness. If you didn't have that kind of interaction going on all the time between water molecules, trees would never be able to get water to get from the ground and the roots up to the upper branches of a tree. Okay? Literally what's happening is the water molecules that are in the roots are interacting, they're making hydrogen bonds with compounds in the roots to help pull them up out of the water. Paper towels pick up water, right? It's the same concept. You put a paper towel, a little bit of water, the water from a little puddle will move into the paper towel out of the puddles, because when you pull one water molecule in that solution, 3 others get pulled along with it. And others that are attached to those 3 others get pulled in turn. Right? So it's water's cohesiveness, it's stickiness that allows you to have capillary pressure, which is what we're talking about here in terms of getting water to go up from the bottom of a tree to the top of a tree. Have you ever stopped to consider what limits the height of trees on our planet? I bet you it's never occurred to you. Maybe a couple of you have contemplated this. This sounds to me like a beer-inspired contemplation, right? Yeah. Why are trees, what's the tallest a tree can get? Well, I don't know, about 500 feet. Why can't a tree get to be 1,000 feet? What's up with that? You know what governs the maximum height that a tree can reach? It's rooted ultimately in how cohesive water is. If water was more cohesive, then you could get water up to the top branches more easily. But there's only so much that the stickiness of water can do, right? It's not totally sticky, right? It's not irrevocably sticky. These hydrogen bonds form and disassociate all the time. If they formed with a higher affinity than they do, trees could be taller than they are. That's what limits the heights of trees. It's essentially the limit of what you can get away with, relying upon capillary pressure, relying upon the stickiness of water. So that stickiness is pretty cool. Here's a pretty picture from your textbook. This is showing you another ramification of the stickiness of water. That's a water strider, we'll call it. It's not my kind of biology, right? I'm a molecular biologist, some sort of spider, something. But look at that. You know what it is? It's sitting on water, right? It's sitting on water because water has a remarkable surface tension. Water's surface tension is ultimately rooted in the stickiness of water. Those water molecules like to interact with other water molecules. They really like to interact with other water molecules. And if you try to stick something into a water molecule that isn't sticky in the same sense, that isn't going to be engaged in polar bonds, hydrogen bonds, if you can find some molecules that water doesn't like to interact with, water will actively exclude those things. It pushes them aside. It says, no, I'm really happy talking to this water molecule over here. You go find something else to interact with. Right? And so what's going on the tips of the legs of this insect, I'm on safe ground there, right? On the tips of the legs of this insect are molecules that are hydrophobic. They're afraid of water. They don't have any partial separation of charges. And because they don't, water says, gee, I'm really happy. Don't be messing up my deal here. I have this really cozy, happy relationship. I'm nestling my little bit of negative charge up against this water molecule's little bit of positive charge. Don't bum me out here to separate us. We like having this interaction, and so it excludes those other molecules. That lets insects like this walk on water. It's also responsible for water forming drops, right? As opposed to just laying out flat on a surface. The cohesiveness of water, the stickiness of water actually pulls water molecules together, mounds them up, it fights gravity. It's an indication of how strongly, how keenly water likes to stick to and interact with other water molecules as opposed to other things. It fights gravity, goes up trees, trunks, it pulls itself together when you have it on a flat surface. Water tension is another manifestation of this cohesiveness of water. And so, I've been beating this cohesiveness thing to death for the last, 5-10 minutes? It's time now to talk about something else about water that's related to its stickiness, but has a different manifestation. Let's talk about some of the energy that's associated with water. And let me start first by talking with you about this idea of specific heat. Changing gears a little bit, another little bit of chemistry jargon for you, this concept of specific heat. It's a pretty straightforward, simple idea. Specific heat is the amount of energy that it takes to heat something up. Okay? That's a simple way of putting it. Temperature is ultimately, maybe even superficially, a measure of how quickly molecules are moving. Right? When molecules are moving fast, we say that thing's got a high temperature. When molecules are moving slow, it's got a lower temperature. So temperature is a measure of the speed with which molecules on an object or a glass are moving around. Okay? To get water molecules to move faster than they already are, that's code for to raise the temperature of water. You need to invest more energy than you do to just about any other compound, period. Okay? To get 1 gram of water to increase its temperature by 1 degree centigrade, okay, you need to invest 1 calorie of water, 1 calorie of energy. I've got water on the brain right now. It's a medical condition, isn't it? But so check it out, right? That's a formal definition. To increase the temperature of 1 gram of water, 1 degree centigrade, you need to invest 1 calorie of energy. Excuse me. That's the definition of a calorie. How much energy you need to use to raise the temperature of 1 gram of water, 1 degree centigrade. The specific heat of water is 1. It is the benchmark. Everything else gets measured relative to water. We say the specific heat of water is 1 because, by definition, to raise 1 gram of water's temperature 1 degree centigrade, you need to invest 1 calorie of energy. In contrast to what? Just about any other molecule that you would toss out is going to have a lower specific heat associated with it. Ethanol is one that gets mentioned in the lecture notes. It's one of my personal favorite molecules. We'll talk about it several times during the course of this semester. Ethanol's specific heat is 0.6 calories. Okay? To get ethanol to get hotter, to get those molecules moving around faster, to increase the temperature 1 degree, how many calories do you need to burn to get 1 gram of ethanol to go up 1 degree centigrade? 60% what you have to invest to get water to go up 1 degree per gram. All right? It's easier to heat up ethanol than it is to heat up water. It takes less energy to get those molecules moving around faster. Methanol is another specific example that the lecture notes give. To get 1 gram of methanol to increase its temperature by 1 degree, you need less than half of a calorie, 0.4 calories per gram. All right? So what's the deal? The deal is this, is that to get these water molecules to break those hydrogen bonds, to dissociate, you really got to juice the system up. You really got to pump it up with a lot of energy of motion. You have to heat it up more than if you didn't have that number of hydrogen bonds going on between each of the molecules in your vessel or on your table or whatever, right? It's ultimately because each of those water molecules is connected to 4 other water molecules. If it was only connected to 3, it would be a lot easier to get water molecules to move around faster than they are. But they're connected to 4, and it's a pretty small molecule. High density of connectedness per surface area of the molecule, that makes it hard to get water molecules to heat up and to move faster. And so, as a result of that, we get things like this, another figure from your textbook that just shows this idea that temperature buffering from water manifests itself in a couple of interesting different ways. Look at the change in the temperature from the coast of Southern California to inland California. Why is it that it's comfortable 70s right on the coast and really uncomfortable hundreds a little bit like 50 to 100 miles further inland? It's ultimately because that water of the Pacific Ocean is a phenomenal heat sink. The air may get really hot, but when it's close to the ocean, that energy of the hot air molecules ends up getting dissipated into the water of the ocean. You'll lose some of that energy associated with the air molecules, and the less moving air molecules have a cooler temperature, more comfortable to you and I. You don't get that same benefit further inland, where the air molecules now don't have water to transfer their energy to. Because of that, they just keep moving fast, and you feel really hot. Right? So that's one manifestation of temperature buffering. But another manifestation of temperature buffering comes from talking about just the temperature changes to water. It takes more energy to make those water molecules on the right come apart than just about any other molecule. Right? So you have to invest a lot of energy to get these guys to move. What do you suppose happens when you get a water molecule finally heated up to the point where it's moving really fast? So fast that it can break free from all of its water molecule brethren. Right? It breaks all 4 of its hydrogen bonds. We got a word for those kinds of water molecules. We call call that steam, right? Water molecules that are moving so fast that they can get away from they can shed all of their cumbersome hydrogen bonds, right? They're free, they've shed that coil that's been holding them in context and in place with all these other water molecules. When they get heated up finally to the point where they can break all those bonds, they fly away as steam. Technically, we say that they've evaporated. When a water molecule evaporates, this is pretty cool. What's special about the water molecules that are evaporating? Those are the water molecules that have the most energy associated with them. Those are the ones that are moving the fastest, fast enough that they can break free of all of those hydrogen bonds. When they leave the party, what do they take with them? All that extra energy. And what do they leave behind? They leave behind the water molecules that have less energy. And so, when water molecules evaporate, they do a remarkably good job of reducing the temperature of the water molecules that stay behind. That's another way that water acts as a temperature buffer. Fast-moving, hot water molecules get out of dodge. Slower-moving, cooler water molecules stay behind. Why is it that for the last 5 days, when it's been over 90 degrees here in Dayton, we've been sweating like pigs? We're doing that. That's supposed to be a little chuckle. I've mesmerized you now with my talk about my monotonous talking about water. You sweat because that's a really effective means of maintaining your body temperature in a cooler as opposed to a warmer state. When you're cold, you don't sweat. You know why you don't sweat when you're cold? It's because if you were sweating when you were cold, you'd get colder still because the water molecules that had the most energy would be evaporating away and you'd get colder. When it's cold, you have well-designed bodies, you don't sweat. When you're hot and your body temperature is getting a little too warm, we have bodies that are designed to cool themselves off by the most efficient means available to us all the time, and that is shedding water molecules and getting rid of the ones with the most energy to leave behind those with less and keep us cool, or at least cooler. Isn't that an amazing system? There's no other molecule that would work so well for that purpose as water. Amazing stuff. Great temperature buffering because of this specific heat. Now, I've been talking about what's going on the right side of this picture, right? You guys, I think, are already ahead of me. You've contemplated what the whole story is here, and you've seen another facet, still another wonderful way. Hey, that's appropriate music. No, it's okay. There's still another way, one more way, that water acts as a great buffer for temperature. Check out what's happening on the left-hand side. Ice, right? So you guys all know water can be in 3 different states. It can be a gas, it can be a liquid, and it can be a solid. When water is a solid, we call that solid ice. Interesting thing about ice as opposed to liquid water. Check out the way they've tried to represent it for you here. Look, this guy, that one water molecule, looks like it's only got 2 hydrogen bonds, right? To this one and to this one. Well, I don't know, there must be one that has 3. Yeah, here we go. Here's a water molecule that has 1, 2, 3 different hydrogen bonds. At most, a water molecule can have 4. The higher the temperature, the fewer the number of hydrogen bonds, right? So liquid water has this sort of interesting relationship. Water molecules are kind of V-shaped, right? You can see that in the pictures here. And if you have 2 water molecules, there's kind of a, the V's can get up against each other in their crotches and so forth. So you can kind of pack water molecules together in a higher density when they're able to move around. But when you take away energy from those water molecules and they get locked in to a 4 hydrogen bond state, right? So they can't, the crotches are no longer bumping into each other. When you get into that sort of interaction where each water molecule is engaged with by four hydrogen bonds with other water molecules, that gets to be a rigid structure. And they're not able to sort of buff it up against each other and in little patches get a higher density. That stable relationship, the long and the short of it is this, that stable relationship in ice causes the water molecules on average to be further apart from each other than they are when they're jostling up against each other in liquid water. That's the key, right? They have a lower density. Cubic space for cubic space, there's fewer water molecules in ice than there are in liquid water. Things that have less density than other things float. They weigh less. They float. Ice, did you need me to tell you this? Ice floats. You guys had this all figured out already, right? But ice floats. The slowest moving water molecules, where do we find them? On a lake in the winter. The slowest moving water molecules on a lake in the winter are at the very surface of the lake. Why? Because ice floats. It has a lower density. But wait a minute. Evaporative loss of heat, how does that work? Highest energy molecules fly away. Where are they? In a lake in winter. The high energy water molecules, the ones moving around the most, the ones with the highest temperature. They are underneath a physical barrier of ice. The molecules with the lowest energy, they cannot escape. They can't fly out into the atmosphere and take their energy with them. They can't leave Dodge. They are stuck in the lake. Whoa, right? Just think what would happen if ice was heavier than water, if lakes froze from the bottom to the top. If that was the scenario, lakes would freeze a whole lot faster than they do. And in fact, almost every lake in this part of the world, including the Great Lakes, would be completely frozen from bottom to top by the end of the winter. But because we put this layer of low energy water molecules on the top of the lake to act as a barrier, in some sense, to prevent the high energy molecules from escaping, fish can hang out in the watery part of the lake, most lakes, all winter long. Isn't that amazing? Just think, if that little quirky thing wasn't there, how different life would be on this planet. If water was less dense than the solid version. Doesn't that seem counterintuitive? What do you think is less dense, a rock or lava? Rocks sink in lava. Most solids are denser than their liquid form. Water is almost unique in that respect. And it's ultimately because water has this remarkable tendency or keen interest in making so many hydrogen bonds per molecule. There's very few other molecules that are like it. So water has this amazing temperature buffering ability. You see it in terms of weather patterns. You know, oceans are a nice heat sink. That's cool, literally. We see it in terms of evaporative loss of heat when you're trying to cool your bodies off by sweating. We see it in this temperature buffering that's separate and apart from that comes from the fact that ice is less dense than liquid water. Remarkable stuff. And remember, I set you guys up at the start of today's lecture. I was telling you that it's hard for a biologist, or anybody for that matter, to even conceive of life in the absence of water. Okay? That cohesiveness comes in really handy for things that living things like to do. Move water from one place to another, like we see happening in trees. Walk on water, like we see happening with insects walking on water. Temperature buffering. Our bodies are designed to work best in a very narrow temperature window. If your body temperature goes up, We got a word for that. We say you've got a fever. You know how much your body temperature needs to go up for us to start saying you've got a fever? It's like 1/10 of a degree centigrade, just a little teeny tiny bit. If it goes up 2 or 3 degrees, we start giving you medicine to keep your temperature in check, to lower it down. If it goes up 5 or 6 degrees, we start putting you in ice baths because you're starting to be on the verge of a serious condition, an irreversible kind of condition. If it goes up 10 degrees, there's a clinical term for people whose body temperature went up 10 degrees or more. Dead. Right? That's the word we use to describe somebody who's had this problem. That's how narrow a window we have. There's also a word for people whose body temperature has gone down 10 degrees. It's the same manifestation. It's also called dead. Right? We got this really narrow range that we can work in optimally, or at all for that matter, and water is one of the keys for us being able to maintain that optimum temperature. And we're not the only living things that we know operate best in a narrow temperature range. Bacteria have preferred temperatures. If you heat them up or cool them down 10 degrees or so on either side, that usually results in the same death of those bacteria. Plants have a pretty broad range, right? But even still, if you bring them down to minus 20 degrees centigrade, or you take them up over 100 degrees centigrade, they're dead, cooked or frozen, one way or the other. But it's a narrow range. Water is alone in terms of molecules that let us maintain that temperature. So remarkable stuff for water. And that's not all, because water is also, bar none, the single best solvent that we know. A little more chemistry jargon for you here. A solvent is something that dissolves other things. A solute is the thing that gets dissolved by a solvent. Okay? Water is an exceptionally good solvent. Nothing else can dissolve as many different kinds of solutes as like water. Water stands apart. You know, the alchemists in the Middle Ages, the Dark Ages, had this passion. Their ambition was ultimately to find something that would change base metals into gold or silver, right? And a secondary ambition was to find a universal solvent. They wanted to define specifically something that they called aqua regia, a water, something that could dissolve gold in silver. That's one of the things that makes gold such a permanent thing once we've made it into a ring or something like that, or a coin. It turns out water can't really dissolve it. The alchemists were looking for something that could dissolve stuff like gold and silver. They never found it. They never found something that was better at dissolving noble metals like gold and silver. Even acid can't do a number. Hydrochloric acid would have a lot of effect on the skin and bone, but my ring would be largely unchanged if we stuck my hand in a vat of hydrochloric acid or of base, for that matter. Right? Water is the best solvent that we can find, despite many alchemists over the years looking for something better. Let me tell you now why water works so well as a solvent. Here is a picture of a beaker of water with some sodium chloride. You guys all know what sodium chloride is. General public, we refer to that as salt. It's table salt. Right? What do you guys remember about sodium chloride from Thursday? Right? We've got here a scenario where there are sodium ions that are hanging out with chloride ions. Why? Well, because the sodium has a full positive charge, the chloride has a full negative charge. That got set up because chloride ions, chlorine, is so much more electronegative than sodium is. Going back to the beginning of the lecture and what I talked with you about on Thursday, chlorine has just one electron to go to fill out its outermost shell. Sodium has just one lonely guy floating around in its outermost shell. It's really happy to pitch that thing onto something else, and chlorine is delighted to receive it. Right? So chlorine is much more electronegative than sodium, so much more so that it doesn't make a covalent bond, not even a polar covalent bond with unequal sharing. The chlorine just takes the electron and says, mine, and keeps it all to itself. There's no more sharing of that electron. The sodium goes off on its own. The chlorine has one extra electron. That's called an ionic bond. So the sodium has this really intense positive charge associated with it. It's down an electron. And the chlorine has a really intense negative charge associated with it. It's got one more electron than it has protons in its nucleus. Check out what happens when water has a chance to interact with something like sodium chloride, with salt. All right? Look what happens. Big old honkin' negative charge. Water has these partial positive charges associated with each of its hydrogen atoms. Right? So each water molecule has two partial positive charges, each associated with its hydrogen atoms. Water has this itch that it wants to scratch. Gee, I got this little bit of positive charge over here. What can we do about that? Oh, you know what I could do? I could rub up against and get nice and cozy with something with a little bit of negative charge. Wouldn't that feel good? Opposites attract, right? Those charges start to offset each other a little bit. And around that one chlorine ion with its full negative charge, you can have, what, it's showing you 1, 2, 3, 4, 5, 6, 7 water molecules, and you're not getting the three-dimensional look at this. Each of those fully negatively charged chlorine ions can have on the order of a dozen or so water molecules rubbing each of their two positive, slightly positively charged hydrogens up against it. The chlorine feels good because it's got this negativeness that's just not right. Separation of charge is something else nature abhors. So the chlorine's feeling pretty good. The water's feeling pretty good. The water's even happier to rub its little bit of positive charge up against this really manly negative charge, right? And so it's willing to even break some of its hydrogen bonds with its friends. It's like, yeah, you're cool. I like hanging out with you, but did you see that guy over there? That's where I'm heading, right? And so the upshot of all of that is the chlorine goes into solution. It's dissolved. It gets picked up by the water molecule, and the chlorine says bye to the sodium that it had been interacting with to offset the charge, and they're gone. And they never see each other again. And at the same time that that party's going on with the chlorine, this studly chlorine, the foxy sodium is getting a lot of attention from the little bit of the negative charge associated with the oxygens on these other water molecules. Water molecules, again, they can go either way. They can give electrons, and they got a little bit of positive, a little bit of negative, right? These other water molecules are really impressed by that full positive charge associated with the sodium. They rub their negatively charged oxygens up against it. They're feeling good. Everybody's happy here. The sodium chloride is no longer a little crystal. It's no longer a solid. It's gone into an aqueous solution. It got dissolved by the water molecules. If water didn't have those partial separation of charges, it couldn't do this, right? If there was no separation of charge between the hydrogen and the oxygen, there would be no basis for interacting between a water molecule and a sodium or a chlorine ion. But there is a partial separation of charge, and that in turn allows the water molecules to bring sodium chloride up into solution. It is an exceptionally good solvent. Water can dissolve things that have a positive charge. Water can dissolve things that have a negative charge. Water can dissolve things that have a little bit of a positive charge and a little bit of a negative charge. The only thing water can't dissolve is stuff that has no charge. Right? Again, we'll talk more about that in lecture on Thursday when we get into organic chemistry, but oils and fats and things like that, one of the things that really distinguishes those molecules is that they are rich with non-polar covalent bonds. Water doesn't know what to do with things that have non-polar covalent bonds. It loves ionic bonds. It loves polar covalent bonds. It likes hydrogen bonds. Non-polar, not its cup of tea. Right? doesn't mean that there's not a place in the world for things that are milk toast. They like to interact with other things that are milk toast, and we'll talk about that on Thursday. But water does a bang-up job of dissolving something like sodium chloride. What do you get when you put sodium into water? You get salty water. Water is a very effective solvent. And it's, again, ultimately because water has that little bit of negative charge at one end and a little bit of positive charge at its other ends. All right, so water, a remarkably good solvent. No other solvent works on its broadest spectrum of solutes and dissolves as much solute per volume as water does. Okay? If you tried to dissolve salt, sodium chloride, in ethanol, you know what? You'd find ethanol's a pretty good solvent. It dissolves a lot of sodium chloride. But if you tried to dissolve, if you had a liter of ethanol and you tried to dissolve sodium chloride in the liter of ethanol, you'd find that you could dissolve more sodium chloride in water than you could in ethanol or methanol or any other solvent that you like. Water does the best of any job at being a solvent in that kind of circumstance. Now, it's time, I suppose, for me to talk with you a little bit about this idea of concentration. And let me see if I can't make this particularly relevant to you as you begin to contemplate going to the labs this week for the first time in this class. This week's lab is all about pH. Okay? And where I want to go in the course of the next 15 minutes or so is I want to take you by the hand and make sure you're all comfortable and on the same page as I am talking about pH. Okay? To talk about pH, I got to start by talking about concentrations. Okay? How much solute got dissolved in a solvent? Okay? This is a lecture all about water, so the solvent here is water. How much gets dissolved? Well, to make this, to be able to compare apples to apples, let's talk about molarity. Okay? A mole is a specific number of molecules. It's Avogadro's number of molecules, 6.03 times 10 to the 23rd molecules. An inconceivably large number of molecules, but that's what a mole is, 6 times 10 to the 23rd molecules. What makes this a convenient way to think about matter and molecules, why even bother talking about moles, M-O-L-E, why we talk about moles, is because this interesting phenomenon. Sodium chloride, let me make sure I get the numbers right here. And while I'm doing that, let me also point something else out to you. Did you guys notice I don't look at my lecture notes that much? Right? But once in a while, I'll look at my lecture notes. I'm looking at my lecture notes right now. And that's because off the top of my head, I didn't recall the molecular weight of sodium chloride. It's 58. You just saw that in my lecture notes. This is an aside, a bit of a digression. I don't know the molecular weight of sodium chloride off the top of my head. You guys shouldn't worry about knowing the molecular weight of sodium chloride for the first test in this class. If I got to look it up in the lecture notes, I'm telegraphing to you. I need for you to notice that and for you to realize, oh, I guess I don't have to worry about that. Right? That's a little bit too minutiae, a little bit too much trivia. I'm not wasting my brain cells on it. You shouldn't either. I'm hoping that you guys, but notice how I don't look at my lecture notes all the time because I'm talking about concepts, underlying principles, things that, I think I just have wrapped my head around it. I understand. That's the sort of stuff I hope you guys get ready for on the first test in this class, not the molecular weight of sodium chloride, which I happen to now remember is 58. So end of the digression, back to the point at hand here. If you gave me 58 grams of sodium chloride, and again, 58 is a magic number for sodium chloride because that's its molecular weight, the total number of protons and neutrons of sodium and chlorine added together equals 58. If you gave me 58 grams of sodium chloride, you would have delivered to me 1 mole of sodium chloride molecules. 6 times 10 to the 23rd molecules of sodium chloride are in 58 grams. In contrast, let's talk about a different compound. Instead of sodium chloride, let's talk about sodium hydroxide, NaOH. Sodium hydroxide has a molecular weight of 40. If you gave me 40 grams of sodium hydroxide, you would have given to me 1 mole of sodium hydroxide. I don't remember sodium hydroxide's molecular weight. I looked at it at the same time I was looking at sodium chloride, so just so you know, behind the curtain here a little bit. All right? But if you give me 58 grams of sodium chloride and a liter of water, I can dissolve 58 grams of sodium chloride in water really pretty easily. And we got a word for that kind of solution. When you've dissolved 1 mole of a solute in a solvent, solute here is sodium chloride, solvent is water. When you dissolve 1 mole of sodium chloride in 1 liter of water, that water we now say is a 1 molar, M-O-L-A-R, solution of sodium chloride. Water is dissolved 1 mole. That liter now is a 1 molar solution. If instead of sodium chloride you gave me 40 grams of sodium hydroxide in another liter of water, if I dissolved that in the water, I'd now have a 1 molar solution of sodium hydroxide. Just to make sure you guys are all tracking with me here. Let's do this experiment again, this thought experiment again. And here's, before I had 1 liter of water and 58 grams of sodium chloride. Keep in my 58 grams of sodium chloride, but this time I'm dissolving it in 2 liters of water. All right? What do we call that? That's a half molar solution, because it's the molarity here is the number of moles dissolved per liter. Okay? So 58 grams of sodium chloride in 1 liter, 1 molar solution. 58 grams dissolved in 2 liters, a half molar solution. 58 grams dissolved in 3 liters, a 0.333 molar solution. This is just a touch more tricky, but 58 grams dissolved in half a liter of water. It's a 2 molar solution. Okay? If that doesn't just jive with you right now, rewind this part of the lectures, think about it for another 2 minutes. It's not that hard. All right? But molarity is a measure of the concentration of a solute in a solvent. And strictly speaking, it's the number of moles per liter. All right, enough foundational stuff. Let me get to pH, because pH is a measure of the concentration of hydrogen ions in a watery solution. I've had this picture hanging up behind me for the last 5 minutes talking about concentration. And again, I know how this works. You guys are really smart. You're a couple steps ahead of me, I'm sure. You've looked at that and you say, what's going on over there? You got 2 water molecules on the left. That's what the 2 in front of the H2O is all about, right? There are 2 water molecules there. And somehow or other, it looks like one of those water molecules picks up an extra hydrogen. Can you do that? And the other one has lost a hydrogen. Can you do that? Wait a minute, I thought oxygen always wanted to have 2 covalent bonds. And I thought hydrogen, well, how does this work? Right? Well, it turns out this can happen. Right? You can dissociate. It's ultimately based on the fact that the sharing of the electrons between the hydrogens and the oxygens isn't an absolutely even sharing. Oxygen sometimes strips away that electron. Once in a while, that electron just doesn't make its way back. There's no more sharing. The hydrogen proton now just sort of floats away, and all you're left with is an oxygen with an extra electron and a hydrogen attached to it. We got a word for that. That's called a hydroxide ion, OH minus. It's not a happy situation, but it can happen. When that happens, you got this lone proton floating around looking for something to do. And the easiest thing for it to do is to rub. It's got a full positive charge. It likes to rub up against something. It needs to offset that positive charge. It finds some lonely water molecule that's got its pretty exposed, slightly negatively charged oxygen, and it bumps up into it and says, hey, cutie, I'm hanging with you from here on out. You got a name for that relationship. That's called a hydronium ion. Hydronium ions, H3O, have a positive charge, and the flip side to that is a hydroxide ion with its full negative charge. So that dissociation can happen. It turns out it doesn't happen too much because it's actually not a really, there's really good sharing that's usually happening. It's not a really comfortable relationship for either the hydronium or the hydroxide. It doesn't happen that much. When I say it doesn't happen that much, here's what I mean. It happens, and this is just my photographic memory kicking in. You guys don't have to remember this particular bit of trivia. But this is how rarely it happens. Only one molecule out of 554 million water molecules would have had this separation occur. Right? Not that much. But nonetheless, it happens. In a bottle of water like this, we're probably, it's the molecular weight of water. 2 hydrogens, oxygens, molecular weight. Anybody know oxygen's molecular weight? I'll blame it on you if you get it wrong. 16? That sounds right. 16 for oxygen, 1 for each of the 2 hydrogens, molecular weight of 18. That means in 18 grams of water, we should find an Avogadro's number of water molecules, 6 times 10 to the 23rd. I haven't weighed this bottle of water, but it sure feels like more than 18 grams worth to me. That means I got way more than 6 times 10 to the 23rd water molecules in this bottle. And 1 in 554 million is a teeny tiny fraction of 6 times 10 to the 23rd. In this bottle, there are many millions, probably billions or trillions of water molecules that have dissociated like that. Right? It's all a matter of scale. So, if 1 in 554 million water molecules have broken apart like that, what's their concentration? Right? That's where we're going with all this. What's their concentration? Their concentration is this. In straight up water, like what is in that bottle right now, in straight up water, 1 times 10 to the negative 7th molar concentration of hydronium ions, and also 1 times 10 to the negative 7th molar concentration of hydroxide ions. That's what 1 in 554 million translates to in terms of concentration. 1 times 10 to the negative 7th molar. 10 to the negative 7. 10 to the negative 1, remember, is 0.1. 10 to the negative 2 is 0.01. Right? So give me 6 zeros and a 1. Now we're starting to talk here. It's a teeny tiny concentration. And yet, it is a hugely important concentration from the perspective of living things. Those positively charged hydronium ions and those negatively charged hydroxide ions are essentially loose cannons on the deck. Right? And living things are keenly aware and interested in what their concentration is. We are designed to work in a very narrow range of hydronium and hydroxide ion concentrations. You get a little bit more concentrated than 10 to the negative 7th molar, we got issues. You get a little less concentrated than 10 times 10 to the negative 7th, we got issues because we're relying upon them to facilitate some chemical reactions that we want to take place. So that concentration of hydroxide and hydronium ions is hugely important. Again, in regular old water, 1 times 10 to the negative 7th, let's keep our focus here on the hydronium ions. Chemists appreciate appreciate the importance of these hydrogen ion or these hydronium ion concentrations. And they realize that we need a shorthand to talk about them effectively, right? It becomes really cumbersome. It's awkward. Frankly, I'm getting sick of talking about 1 × 10⁻⁷ molar concentration of hydrogen ions. Oh my gosh, isn't there a shorthand we can use? There is. That's what pH is all about. Lowercase p in italics, turns out, is a widely used symbol amongst mathematicians that chemists have glommed onto for the negative log base 10 of something. About that. The negative log base 10 of 10⁻⁷ is 7. Okay? -7. What's the negative of -7? It's 7. The negative log base 10 of 10⁻⁷ is 7. And so if you put a lowercase p, italics if you can, in front of h, we've got a shorthand now for talking about the hydrogen ion concentration in water. Straight up, plain old-fashioned water. We say that has a pH of 7. That's the concentration of hydronium ions. Now, looking at that equation up there, you guys know that for every hydronium ion, there's going to be a hydroxide ion, right? It also turns out that water with neutral pH has a pH of 7 and a pOH of 7. A little bit of trivia comes in handy for you in the lab and later on as we talk about chemistry and living things. Funny thing, pH plus pOH in any solution always equals 14. pH plus pOH always equals 14. And the math of it works out sort of like this. If you jack up the hydronium ion concentration by pumping something like an acid into the solution, hydrochloric acid, if you raise the concentration of hydronium ion, what's going to happen is hydroxide ions are going to have an easier time finding hydrogens, and their concentration will go down. So if you pump up the hydronium ion concentration artificially, you're also simultaneously pushing down the hydroxide ion concentration. Funny thing, pH plus pOH always equals 14. Last little bit of vocabulary for today. When you've got a pH number that is less than 7, we're talking about an acidic solution. When you have a pH number that is larger than 7, we're talking about a basic solution. Okay? Acidic solutions have more hydronium ion than hydroxide ion. Let's say that the concentration, which is a higher concentration, 1 × 10⁻⁶ molar or 1 × 10⁻⁸ molar? 10⁻⁶ is 100 times more concentrated than 10 × 10⁻⁸. Okay? The pH of something that has a hydrogen ion concentration of 10⁻⁶ molar is 6. It's less than 7. All right? The pH of something with a hydrogen ion concentration of 10⁻⁸ is 8. Its pH is a larger number. So things with a pH higher than 7, larger than 7, are basic. Things with a pH less than 7 are acidic. I've slipped that in on you at the very end. You're going to wrap your head around that a lot in lab this week. It's fuzzy to you. I can see how the math could be a little confusing. Look carefully at the lecture notes, and I think it'll become clear again in a minute or two. All right. Have a lot of fun in lab this week. We'll see you guys on Thursday.